Hello everyone. Today we shall continue part 3 of coordination compound. So in part 1 we have studied what are coordination compound, different types of ligand, and in part 2 we have studied the Arabic nomenclature of coordination compound. So today we shall learn valence bond theory and crystal field theory. So before we start valence bond theory, first of all we shall go back to our first video in which I have explained about Werner's coordination theory. So Werner postulates tell us that metal ions, they exhibit two types of valency, that is primary valency and secondary valency. Primary valency, they are ionizable, whereas secondary valency, they are non-ionizable. And also there are some other points from his postulates. At the meantime, there are also some drawbacks of his postulates, that is, he could not explain why only certain elements form coordination compound. He could not explain the stability of the coordination compound, and also he could not explain the magnetic properties of the coordination compound and the directional properties of the bond. So these are some of the drawbacks of his postulates, Werner's coordination theory. So in order to improve the theory, in order to improve the drawbacks, we have a new theory, that is valence bond theory. So today we shall learn valence bond theory, and also we shall learn to find the magnetic properties, hybridization, and the geometry using the valence bond theory. So first of all, let us know what actually is valence bond theory. So valence bond theory tells us that metal ions under the influence of a ligand uses sp-d orbitals to get hybridized and forms an orbital of definite geometry. So valence bond theory tells us that metal ions under the influence of a ligand uses sp-d orbitals to get hybridized and then form an orbitals of definite geometry. So out here the d orbitals which we have is inner d orbitals or the outer d orbitals. So inner d orbital may be n-1 d orbitals and nd orbitals or the outer d orbitals. And also we should know that the empty orbitals of the metal ions, they overlap with the field orbitals of a ligand and they form a coordinate covalent bond in valence bond theory. So since we are talking about a geometry out here, so let's say if we have a coordination number 4, so if the coordination number is 4, if the coordination number is 4, we can have two types of hybridization, that is sp3 and sp2d. So sp3 will be tetrahedral. You should all remember this one, and this will be square planar. So for coordination number 4, we have sp3 and sp2d. sp3 will be tetrahedral, this is the geometry, and sp2d will be square planar. So again, if we have coordination number 5, we will have sp3d, which will be trigonal by pyramidal. So if the coordination number is 5, we shall have trigonal by pyramidal. If the coordination number is 6, we shall have sp3d2 and d2sp3. Both of them are octahedral. So you should remember the hybridization and the coordination number and the geometry, which I've just written right now. So using this, we shall find the magnetic properties, the hybridization, and the geometry of the coordination compound using valence bond theory. So let's say we have FeCN6 4 minus. So using valence bond theory, we are going to find the hybridization, magnetic properties, and the geometry of this coordination compound. So first of all, the first thing we are supposed to do is to find the oxidation state of the metal ions. So out here we shall put this one as x. 6 minus 1 equals to minus 4. X will be plus 2. So the oxidation state of iron out here is plus 2. So out here we have x equal to plus 2. So the atomic number of iron is 26. So if I write the electronic configuration, I shall have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Since it is plus 2 out here, so I need to remove. So if it is plus 2, I'm going to remove 2 electrons, right? If it is plus 2, I'm going to remove 2 electrons. If it is minus 2, I'm going to take in 2 electrons. Minus, I'm going to take in. Plus, I'm going to remove the electrons. So since this is plus 2, I need to remove 2 electrons. So from the last subcell, from the last orbital, I'm going to remove the electrons. So if I write Fe2 out here, I shall have 4s0, 3d6. So you may ask the question out here, why don't I remove the electrons from here? Because out here when we write the electronic configuration, this is the last one, right? But if you look the orbitals, this is the last orbital. These electrons belong from the last orbitals. But if we look at the way we write, this will be the last one. So always don't get confused with this one. Out here this is 3d, this is 4s. So we are going to remove electrons from 4s first and then from 3d. So if it is Fe2, we shall have 4s0, 3d6. So now I will write in this manner Fe. This is our 3d, 4s, 4p. So we have 4s2, 3d6. Now Fe2, this plus 2 out here. So I'm going to remove 2 electrons. So I'm going to remove 2 electrons from here. So I will have, and again, FeCN6 4 minus. So now, if we look this coordination compound, the ligand out here is a strong ligand. So you may ask again, sir, how do we know which ligand is a strong ligand and which ligand is a weak ligand? So if you look at the spectrochemical series, you will know which ligands are strong and which ligands are weak. So what is spectrochemical series? The arrangement of ligands in the increasing order of their strength. So the last one, if you remember, CO, CN, NO2, En, all these are strong ligands. You look them as a strong ligands, and the rest you can look them as a weak ligand. So CO, CN, NO2, EN, they comes under strong ligand. So out here we have CN. So CN is a strong ligand. So what happens is when the ligand is strong, these electrons, these single electrons, when they come down out here, they pair themselves up. So this is already paired out here. So these two will pair together and these two will pair up together. So these single electrons, they pair themselves up. So now since we have 6 cyanide, one cyanide, another cyanide, cyanide, and cyanide. So you should always remember that if it is a strong ligand, they will pair themselves. If it is a weak ligand, they will not pair themselves up. So now I will write the hybridization geometry and the magnetic property. So out here, 2 cyanides, they enter the d orbital, right? So I can write d2, 1s, and 1, 2, 3. It is from p. So p3. The hybridization will be d2sp3. If it is d2sp3, we have octahedral and the magnetic properties. So out here, these electrons, when you look these electrons, all the electrons out here, this is paired, and this is also paired. There is not a single electrons out here. So all the electrons we have, they are paired up. So if all of them are paired, we shall have diamagnetic. So using valence bond theory, we find the hybridization, we find the geometry, and we find the magnetic properties. So we'll try for another. So now we shall try for CONH36 3 plus. So again, the first thing is to find the oxidation state. So X will be plus 3. Atomic number of cobalt. Atomic number of cobalt is 27. So if I write the electronic configuration, I shall have 4s0, 4s2, 3d7. So I'm just writing the last one only. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So since it is plus 3, I need to remove 3 electrons, then I will have 4s0, 3d6. 4s0, 3d6. Why? Because I need to remove 3 electrons. So out here, x equal to plus 3. So I'll write here cobalt, three D, 4s, 4p. So I have 4s2, 3d, 5, 6, 7, 3d7, cobalt, 3. I need to remove 3 electrons. So I will have 2, 3. So I remove 3 electrons, 2 from here and 1 from here. So I will have 6 electrons. So now we have CO, NH3, 6, 3 plus. 3D 4s 4p. So now if you look this ligand out, if you look this coordination compound and the ligand out here, NH3. So in general, NH3 is a weak ligand, but when it make bonds with cobalt, NH3 it act as a strong ligand. Okay, point to remember is that NH3 is a weak ligand, but when it make bond with cobalt, it act as a strong ligand. So if it act as a strong ligand, what will happen? All these single electrons, they will pair themselves up again. So out here, this is already paired. These two will pair up, and these two will pair themselves up. So whenever it is a strong ligand, they will pair themselves up. So now we have 6 NH3. So I'll put here 1 NH3, 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 NH3. So we have 6 NH3. So now if you look at the hybridization geometry and the magnetic property. So if you look at the hybridizations, NH3 in D we have 2 NH3, so I'll write D2S, in P we have 3, D2sp3. So the hybridization will be D2sp3. If it is D2sp3, we have octahedral, right? And now all these electrons, they are paired. There is not even a single electron, one single electron. So this will be again diamagnetic. So this will be again diamagnetic. So now again we have FeH2O6 3 plus, and if I found the oxidation state of Fe, we have plus 3. Atomic number of Fe is 26. If I write the electronic configuration, I'm just writing the last one. We have 4s2 3d6. So if it is Fe3, or I'll write here Fe3 plus, we shall have 4s0 3d5. Why? Because you're going to remove 3 electrons. So we have x equal to plus 3. So out here Fe d orbital, s orbitals, and p orbital. So 3d, 4s, 4p. So out here we have 4s2 3d6. Again Fe3. So now if it is Fe3, I'm supposed to remove 3 electrons. So 2 from here, 1 from here, I will have 5 electrons. I remove 2 electrons from here and 1 electron from here. So I will have Fe5. Sorry, 3d5. So now again I will have FeH2O 6 3 plus. 3D, 4S, 4P. My ink is about to finish. Okay then. So now H2O, if you look H2O, H2O is a weak ligand. So what did I say? If it is a weak ligand, these electrons, they will come down as they are. They will not pair themselves up, right? Strong ligand will pair the electrons, weak ligand will not pair the electrons. So since H2O is a weak ligand, these all will come down as they are. They will not pair themselves up. And now, since we have 6 water molecules, so 1 water molecule, 2, 3, 4. Still we need 2 more. So we will make 1 more d orbitals out here. Another d orbital, 4d. You make another 4d orbital and you put water molecule out here. So if I write the hybridization geometry, magnetic property. So what will be the hybridization? sp3d2. So I will have sp3d2. If sp3d2, again octahedral, and the magnetic properties. Now the electrons out here, they are single, they don't pair themselves up. If we have even 1 single electrons, it will be paramagnetic. It will be paramagnetic. So it is very easy how to find the magnetic properties, how to find the geometry and the hybridization using valence bond theory. So basically valence bond theory is trying to improve or trying to rewrite the drawbacks of Werner postulates. It's trying to improve the postulates of Werner. So now after this one, again we shall do crystal field theory. We shall learn crystal field theory. Since there are some drawbacks in valence bond theory, crystal field theory will try to improve those drawbacks. So we shall learn crystal field theory now. So now we shall start with the crystal field theory. So crystal field theory is based on electrostatic model, which assume that the metal ion, they act as a point charge. So the metal ions, they act as a point charge. So if we have anionic ligand, it is known as negative point charge. If we have a neutral ligand, it will be dipole. It will cancel each other. So the metal ions, they are assumed as a point charge. So what happens in crystal field theory is that the metal ions and the ligand, they form an ionic bond. So which is mainly based on the electrostatic interaction between the metal ions and the ligand. So out here they are making an ionic bond, whereas in valence bond theory they are forming a covalent bond. So in crystal field theory, we are going to now look at the d subcell. So d subcells, when they are in the, or the d orbitals, when they are in the ground state, they are highly stable. But when the ligands, they approach closer to the d orbitals, their degeneracy or the stability decreases. So now if you look at the d orbitals, let's say this is the d orbitals. Out here we have dxy, dyz, dxz, dx square, y square, dz square. So this comes under T2G and this comes under EG. So these are the d subcells. So what happens is that when they're in the ground state, they are highly stable, the degeneracy is high, so we call them as degenerate d orbitals, right? So but when the ligands they approach closer to the d orbitals, their degeneracy decreases. So their energy, so let's say this is the energy out here. This is the d orbitals in the ground state. So the energy increases out here when the ligands are closer. So what happens is out here the ligands are in the ground state. Out here when the ligands are closer with the d orbitals, there is an increase in energy when the ligands are closer to the d orbitals. So when the ligands are very close to the metal ions, the d orbitals they split themselves into T2G and Eg. Why? Because the metal ions they act as a point charge. Point charge they contain some electric field. These d orbitals also they contain some electric field. So when they come closer to each other, there is a repulsion, and then there is a splitting of d orbitals. So the d orbitals out here split into T2G and Eg. So out here delta naught is the energy gap between these two T2G and Eg, and 3/5 and 2/5 is the energy separation. So out here in T2G we are going to have dxy, dyz and dxz. Out here dx square, y square and dz square. So what happens in crystal field theory is that when the ligand is a strong ligand, their splitting is quite large. There's a larger splitting, whereas when the ligand is a weak ligand, their splitting is lower. So there's a lower energy gap. So in weak field we have lower energy gap. In strong field ligand we have larger energy gap. So why are we learning crystal field theory? So what happens is that in the previous valence bond theory we have learned how to find the geometry, hybridization, magnetic properties, but there was also some drawback of valence bond theory, such as there was too much of assumption in valence bond theory, assuming that if this happens this will happen, right? The type of assumption was too many. It could not explain in details the magnetic properties. We have just written that diamagnetic, paramagnetic, but it could not explain in details the magnetic properties, and also it could not make the exact prediction about the geometry. So there are also some other points of his drawback. So in order to improve his drawbacks, we are learning crystal field theory, where he will try to explain in details all the drawbacks of valence bond theory. So again, the question out here is, using crystal field theory, what are we going to do? So using crystal field theory, we are going to learn to find the number of unpaired electrons in the coordination compound, and also we'll also learn the magnetic properties. So now let's say we have, so all of you, we need to remember this structure out here which I've drawn. So using this one we are going to solve the problems from crystal field theory. So now using crystal field theory, we shall learn to find the number of unpaired electrons and the magnetic properties of coordination compounds. So let's say we have COF6. Let's say we have FeCN6 3 minus. So first of all, I'll find the oxidation state. Fe is 26. We have 4s2 3d6. So Fe 3 plus will be 4s0 3d5. So in d orbitals we have 5 electrons. Our main focus will be only on the d orbitals. So we have energy out here. This is the d orbitals. And this is the energy separation. So out here, Cn is a strong ligand. So whenever previously I have said that if it is a strong ligand, delta naught will be larger. The energy gap will be larger. So let's make it less kind. Out here we have Eg, and out here we have T2G, and this is our Eg. So in D we have 5 electrons, 1, 2, 3, 4, 5 electrons. Out here also 1, 2, 3, 4, 5. This is in the ground state. This is when the ligands are close to the d orbitals, and when the ligands are very close to the d orbitals, they split themselves into T2G and Eg. So now since Cn is a strong ligand, so the energy gap will be larger. And out here we have 5 electrons. So the first 3 electrons will enter out here, and since the gap is too large, the rest of the 2 electrons will not jump to Eg orbitals, they will pair themselves out here only. So if the energy gap is large, the electrons will pair in T2G orbitals only. So when the energy gap is larger, it will jump upside. If the energy gap is large, it will pair in T2G. So delta naught is larger than P pairing energy. We have low spin complex, and the number of unpaired electron is 1, and also since there is 1 electron, single electron, it is paramagnetic. So the magnetic properties is paramagnetic, and the number of unpaired electron is 1. So in exam, if they ask you, they can say, using crystal field theory, find the number of unpaired electrons in FeCN6 3-, and also predict the magnetic properties. So only this much only. It's quite simple. So let's try for another compound. COF6 3-. So we have X 6 into -1 equals to -3, X equal to +3, CO is 27, CO is 4s2 3d7, so CO 3 plus will be 4s0 3d6. So we have 6 electrons in d orbital. CO3 plus, we have 6 electrons. 3 plus means we are going to remove 3 electrons. So now since F is a weak ligand, their energy gap will be smaller. So now we have 6 electrons. So the first 3 electrons will enter T2G. Since the energy gap is smaller, the electrons after filling in T2G will jump to Eg. 3, 4, 5, again will come down 6. So in strong field ligand, the electrons will pair up in T2G, whereas in weak ligand, first 3 electrons will enter T2G, it will jump to Eg, again come down to T2G, and then Eg. So out here, delta naught is less than P. In the previous one, we have delta naught is greater than P. If delta naught is less than P, high spin complex. If delta naught is less than P, we call it as high spin complex, and number of unpaired electrons is 1, 2, 3, 4. We have 4 unpaired electrons, and again it is paramagnetic. So by this we finish valence bond theory and crystal field theory, and also we finish this chapter, that is coordination compound. So if you have any doubt in this chapter, or if you have any problem in this chapter, feel free to ask me in the comment section. I will be always happy to answer your doubt or to clear your doubt.